This session is going to talk about something called digital transducers. Now, till now, we have seen a lot of fundamentals about various types of transducers, various phenomena that are involved, in the operation or designing of the transducers. Now, the why we need something called a digital transducer. These days, if you have observed almost all of our medical devices, they are giving you the information, the display information in some sort of digital displays. For example, you use a BP machine at home, right? So when you are using a BP machine, there is a sensor which is there in that cuff. Okay, you tie it around your the concerned area, and when you are measuring the BP, it is actually giving you certain numbers. Okay, that is easily which is easily comprehensible by a layman. Okay, so now how does analog quantity convert into numbers? If you have seen with the type of sensors that we have been using, they are all analog in nature. Suppose a piezoelectric crystal, it is giving you an output in terms of voltage. Now voltage is an analog quantity, it is continuous in terms of time and magnitude. Okay, whereas the digital displays that you have, they are discrete in nature. That means you need to convert this analog output into some digital form, some discrete form, which can be displayed in terms of some numbers, okay, which can actually be understood easily by a layman or by the end user. Okay, so for that purpose, we need something called a digital transducer, which is converting the analog output into a digital output. Okay, so any transducer that presents information as discrete samples and that does not introduce a quantization error when the reading is represented in the digital form is called a digital transducer. A digital transducer that generates a coded form of measurement is called. Right, so we are going to talk of the most popularly used digital transducers over here. The encoders is actually the most popularly used digital transducer in almost all domains. Okay, because this is simplest to use, very easy to understand, and it is very easy to implant an encoder, this kind of a digital transducer into any device. And almost all the popular devices that you see today, they have some or the other type of encoders included into the circuit, which gives you actually a digital output. Okay, so digital transducer, as we have seen, that it is any transducer that is giving you the information in terms of discrete samples, but it does not introduce quantization error. Okay, and it generates the output in some coded form. So we give it a name encoder. Okay, so the three most popular types of digital transducers that we use in designing the instruments are optical encoder, absolute optical encoder, and sliding contact encoders. So we'll talk about all these three one by one. Optical encoder is basically, you can see the figure. This is what an optical encoder actually looks like. It is a circular disc which has certain slots cut out into it. On the circumference, you can see there are certain slots that are cut out. Okay, and on one side we have a light optical transmitter, that is an LED, and on the other side we have a photo detective device, that is a photo sensor is there on the other side of the disc. Okay, now when this disk is rotating, the LED is on. When the disk is rotating, then the LED, when there is a vacant slot coming in front of the LED, the light passes through, strikes the photo sensor, and the photo sensor generates an electric signal. The very next moment, there is actually a black or an opaque slot coming in front of the LED, which blocks the light from reaching the photosensor. So likewise, when your disk is actually rotating, now this disk can actually be connected to some shaft or some device in your instrument which is actually rotating. It is giving you some value. Right now, with the same speed, when this disk is going to rotate, what will happen? The output that you are going to get is going to be in numbers. Okay, because the how many pulses that were generated, that it will count. Because the output that this photo detector will give you, it will actually be in terms of pulses, because as the disk is rotating, the opaque slots and the vacant slots that are coming in between, they are actually blocking the LED light from reaching the photo sensor. So what happens is there is a kind of pulse train that is being generated. One vacant slot, then one opaque slot, one vacant slot, then one opaque slot. Like this, when it comes in front of the LED, it is something like you have an LED, you cover it with your hand, then you remove it, then cover it, then remove it. So what happens is you see a bright spot, then a dark spot, then a bright spot, then a dark spot. So same thing is happening over here. When your disk is rotating, the LED, it gets one bright spot. So it is a vacant slot. The light passes through, reaches the photo sensor, a pulse is generated. Okay, the very next moment there's an opaque slot, the light gets blocked, the photo sensor doesn't receive any light, and so it gives 0 as your voltage output. So the output that this photo sensor will give you will actually be in terms of some pulse train. Okay, and that pulse we can actually count. You can see in this video that as the disk is rotating, the light is actually alternately reaching the photo detector and blocking. Okay, at one instant it reaches the photo detector, the second instant it blocks. So you can see that as many times the photo detector is receiving a light, or at those many times you can see that a pulse is being generated, which is you have a counting circuit over here which counts that how many pulses have been generated. So like this, you can actually measure the speed, you can measure the position of rotation, and many other data can be measured in terms of numbers. Now this basically this rotation that is taking place is actually due to some physical phenomena may be taking place. Okay, there might be some voltage which is actually making this, maybe it is a shaft connected to some motor or something like that. So that voltage is causing this shaft to rotate. Correspondingly, the disk is rotating, but this optical arrangement and the slots that have been cut out are actually converting your analog input signal that was coming into certain sampled values. Okay, so you can count actually how many pulses were generated or how many samples were generated. So this is a simple kind of encoder disk. Now, a more refined version of the optical encoder is an absolute optical encoder. Okay, now you can see on your screen a figure. This is what an absolute optical encoder looks like. You can see that it has certain concentric tracks, okay, circles, drawn one within one another. So you can see concentric circles are drawn, and the whole circumference is cut into 15 slots. It is divided into 15 slots. Every slot, and how many and you can see that 4 concentric slots are there. So every slot, for example, you see slot 0. Now this particular section 0 again has 4 slots in it. Okay, similarly section 15, you can see that if I see this section 15, this section 15 again has 4 slots in it. Okay, now this actually, what you see over here is, in 0 the pattern of dark and bright spots is something else. For 1 it is something else, for 2 it is something else, right? This black is actually denoting opaque slots, and white is actually denoting open slots. These slots are cut out from here, and black means it is opaque, the light doesn't transmit. So it is some sort of a conversion into binary format. Like you must have seen that in binary, you have combination of zeros and ones, which can, if you have to write 1 in binary, it will be some combinations of ones and zeros, 1 1 0 0 1 1, something like that. Similarly, you have to write 15 in binary, so it will be some combination of zeros and ones. So similarly over here, 0 corresponds opaque and 1 corresponds a bright spot, right? So an absolute encoder, it has many pulse tracks on the transducer disk. When the disk of an absolute encoder rotates, several pulse trains equal in number of the tracks of the disk are generated simultaneously. So at a given instant, the magnitude of a given of each pulse signal will have one of the two signal levels. It is either it will be as determined by the level detector, it will be binary in number. The signal corresponds to a binary digit. That means some number written in terms of zeros and ones. Okay, and so the set of pulse trains gives an encoded binary number at that particular instant. Now, if you have to see over here, you can see that when the light is falling, the first, as per the slots that are cut out, the bright one corresponds to 1, the black one corresponds to 0. So over here you can see that as the light falls, whatever slot is coming in front of the LED, that corresponding binary number gets generated and is passed on. Okay, so this actually is more useful when we are using certain motors which are, which show angular movement, and wherever we have to actually judge the angular movement of the disk. Okay, so for example, if I see from this figure, when it is like the zero that you can see, the slot 0, this will actually correspond to a binary number saying 1000. Okay, or maybe the other way around, that is from the outer circumference, if we count, it will be 0001, right? So, and when suppose for example, when the light falls on over here, the detector that we have, suppose it is getting the value 1110. Now this 1110, if we see over here, it actually corresponds to slot number 15. So if at the output of the absolute optical encoder, the output that we are getting is in terms of 0001, it corresponds to slot number 15, we come to know that the disk is, rotated almost 360 degrees, and it has reached the 15th slot, right? So the other thing could be, if suppose at the output you are getting 1111. So if on the disk, if you see, all ones corresponds to slot number 7. Okay, so we come to know that this disk has made an angular movement in such a way, by such a magnitude, that it has moved from position 0 to position number 7. Okay, so for example, if I say that all these slots, they correspond to, maybe suppose just for an example, if I say if it is 5 degrees, so this whole thing, if it has reached slot number 7, so the angular movement that this disk must have shown would be 7 into 5, that will be probably 35 degrees. So just as an example, I'm saying. So over here actually we can see that if suppose that this is cut into 15 slots. If we see over here, if the total disk is cut into 15 slots, that means the total 360 degrees has been divided into 15. So every slot actually corresponds to 24 degrees. That means if the output value moves from 0 to 1, your disk has actually moved in that particular direction by 24 degrees. Okay, so like if we were talking of all the ones coming in, so that will be 24 degrees multiplied by 7, and that is 168 degrees. So from 0, if your answer or the digital value that you are getting corresponds to all ones, which corresponds to the 7th slot on this absolute encoder, that means from the 0th position, your disk has actually rotated 168 degrees. Okay, so this is what absolute encoder works like. Right, or here you can see in this video that as there is an angular movement taking place, the value changes, the binary number that you get, it changes. Then from parallel to serial, it is converted and it is transmitted in terms of some binary number. So this is absolute optical encoder. It is giving you the value of absolute displacement in terms of some angle. Okay, then the third one is sliding contact encoder. Now this is actually uh, very useful when it comes to making your measurements directional sensitive. Okay, this is actually made up of a disk. You can see on the in the figure, this disk is made up of some electrically insulating material. Okay, and the slots that you see over here in the optical encoders, we used to have cutouts. That means we used to have a vacant slot cutout from where the LED light could pass through. Here in Spain, instead of a cutout, we are having conducting areas. So the slots, the orange colored slots that you see over here, these are conducting areas, and the other areas in the disk are actually electrically insulated. They do not conduct. And two, you can see wires that are output A and output B. As you see, they are connecting wires. And so when this disk is going to rotate, okay, when the output A and output B wires, they are touching the insulating area, there will be no output. And when they touch the conducting area, we get a pulsed output. Okay, see something like this. In this diagram, you can see as the disk is rotating, we can see that blue and green colored, you can see the pulses are being generated. See over now, the two were insulating, blue gets touched first. So the blue wave is actually leading the green wave. Okay, because the blue one, see now, this is corresponding to 0. Now this corresponds to a high. Okay, again it corresponds to 0. Again now it corresponds to a high because it touches the conducting area. Okay, so likewise we can measure in this the rotation that is taking place. Now, as I was telling you about being a directional sensitive, over here, if we can see that the blue colored wave is leading. That means whenever the motion starts, the blue colored electrode or the blue colored pin actually comes in contact with the conducting area first. That means the movement is actually taking place clockwise. If the movement would have been taking anti-clockwise, the green wave would be leading instead of now you can see there is a slight delay in the green wave. That means the blue pin actually comes in contact with the conducting material first. That shows it is a clockwise movement. Had it been an anti-clockwise movement, the green pin would have come in contact with the conducting material first, and the green pin would have started giving the output before the blue pin. Okay, so this is helping in making directional sensitive encoders. So all the conducting areas, they are connected to a common slip ring. The constant voltage is applied to all the slip ring using a brush mechanism. The sliding contact, such as a brush, touches each track and the disc rotates. A voltage pulse signal is picked up from there. The pulse pattern depends on the conducting and non-conducting pattern of the track, as well as the nature of rotation of the disc. The signal representation is done as it is for the optical encoders. Okay, so it has certain advantages. It is highly sensitive, simplicity of construction. It is a very low cost device. However, the drawbacks are contacting and commuting devices. Friction is there. Okay, sometimes the brushes, they bounce due to vibration. So the basically the transducer's accuracy is dependent on the precision of the conducting patterns of the encoder disk. Okay, so the three types of encoders, that is, one is the optical encoder, which we have seen. It's a disk with certain slots cut out. We have an LED, and we have a photo receiving device on the other hand. Okay, so which generates the rotating movement into certain pulses. Then we had absolute optical encoder, which was giving me the rotation values in terms of certain angular values, which is denoted in binary numbers. And the third one that we have is a sliding contact encoder, where we have a complete insulating disk, and we have certain slots, conducting slots in between. Two pins we have, which when they come in contact with the conducting area, they initiate a electric pulse, and that pulse can be recorded. In 1 minute, how many pulse were generated, that we can record that how much rotatory movement must have taken place in 1 minute. Okay, so these are the common devices called encoders. or these are the digital type of transducers which are actually changing the analog output that we had got from the various transducers into certain digital numbers. Okay, so this is helping us in creating a digital display. So all these encoders today in today's biomedical instrumentation, all these encoders are actually a very important part of almost all the instruments.